In this lecture, we discuss how we can estimate the shape of a filter's frequency response when we know the location of the filter's poles and zeros. To start, let's suppose that we have a causal filter which has two poles inside the unit circle. These poles are complex conjugates of each other, so the region of convergence is outside the radius of these poles. Since poles are essentially where the magnitude of the function in the z-plane goes to infinity, you can imagine that the function in the z-plane is a circus tent with poles at the indicated locations and with a canvas that slowly slopes to the ground as the canvas gets infinitely far away from the poles. To find the frequency response of the filter, we want to find the height of this canvas at the unit circle. As you might guess, the magnitude of the frequency response will be greatest where the poles are closest to the unit circle. In this example, the unit circle is closest to the poles here and here. If we mapped out our estimate of the magnitude of the filter plot, we would guess that the filter's magnitude would be greatest near omega p and least on the far side of the unit circle. So this might be an acceptable sketch of the magnitude of the function. The filter would have maximum magnitude at negative omega p and omega p and slowly drape down towards zero. Because there are no poles on this plot, we would also have to make sure that the sketch never reaches zero. Now, let's imagine that we add two zeros on the unit circle. If we add zeros on the unit circle, the magnitude of the z-transform should behave like a circus tent that has two stakes driven into the ground at the 0 points. Therefore, from this plot, we know that the magnitude of the frequency response will be 0 at negative omega p and omega p. We can also guess that the magnitude of the frequency response will be greater at frequencies that are far away from the zeros. Therefore, we might guess that the magnitude of the filter might look something like this. The filter would be 0 at negative omega p and omega p, and would increase to a couple local maxima away from the location of the zeros. If the poles were not on the unit circle, then the frequency response would not go to 0 on the unit circle, but the frequency response would simply be attenuated. In summary, we can estimate the frequency response of a filter by looking at how close each point on the unit circle is to each pole and zero. The magnitude of the frequency response will be greatest near the poles of the filter and lowest near to the zeros of the filter.